Welcome to today's online class on the alcohols. And we're on chapter 19 and we're going through this very, very important section on organic chemistry. And make sure you're going through all of these topics and going back over the stuff we did yesterday and the day before, because the work will accumulate. Let's go down to the homework question. Question 268. We're asked to write down the names and structure formulae of the first four members of the alcohols. And this is quite straightforward. It's simply the same as drawing an alkane, except you're replacing one of the hydrogens with an OH group. Methanol is the first member, CH3OH is how the molecular formula would generally be written, with the OH separated from the rest of the molecule, because that tells us we're dealing with an alcohol. Our second member is ethanol. There's a structural formula. C2H5OH is its molecular formula. That's the alcohol in beers, wines, and spirits. Our third member is propanol, sometimes referred to as propan-1-ol. It's probably more correct to refer to it as that, because there is an isomer of propanol or propan-1-ol, which is propan-2-ol. They're not the same compound, of course. So that's C3H7OH. And my fourth alcohol here is butanol. Butan-1-ol is sometimes that's referred to also. So we have C4H9OH as its molecular formula. Okay, so that's question 268, 269 is distinguish between a primary alcohol and a secondary alcohol. Well, a primary alcohol, and this is a definition we must know, is if a carbon atom, the carbon atom that the OH group is bonded to. Now, if you look at this structure here, there's the carbon atom that the OH group is bonded to. There it is there. That carbon atom itself is bonded to one other carbon atom, and there's the carbon atom itself. So that's the definition of a primary alcohol, and propan-1-ol or propanol is a primary alcohol. Now, if I switch the OH group with either this hydrogen here or that hydrogen down there, well, you can see I get a different scenario coming in altogether. Now the carbon atom that's bonded to the OH group is itself bonded to two other carbon atoms. Here it is, there's the first one, there's the second one. That therefore is called propan-2-ol. It has the same molecular formula, C3H7OH. Sometimes that formula will be written as follows: CH3CHOH CH3, a more expanded version. That first CH3 is that CH3 there, I'm outlining. Then we CHOH, CHOH. That OH is in brackets to show that it's bonded to the second carbon. Okay, and we have a CH3 at the end. So it's pretty easy to generate when it's in the more less condensed form, should I say. But it's harder to generate when it's in the condensed form. So my definition of a secondary alcohol is if the carbon atom that the OH group is bonded to is itself bonded to two other carbon atoms, then that is referred to as a, well, I should say secondary rather than primary. I'll change that after the video. I think you know what I mean there. Question 270 says, how does ethanol come to be present in the body? For a lot of people, it's beers, wines, spirits. Even if people don't drink alcohol, it's pretty difficult to avoid. It'd be in medicines, mouthwash, and so on. And in part B, we're asked to write a balanced chemical equation for the fermentation of glucose. So this is the production of ethanol from fermentation, the process. So what effectively happens here is that glucose, yeast feeds off it, produces ethanol and carbon dioxide as a byproduct. And this is how it's produced in the industry by all the major companies. And we place the two in front of the two products to generate a balanced equation. Let's move on now to discuss the properties of the alcohols. One property we're going to look at is the boiling point of an alcohol relative to its corresponding alkane. Now, why would we compare it to an alkane? Because, as we stated before, there's only one difference between an alcohol and an alkane, and that's an oxygen atom. But it's a major difference, and we'll show when we go through this diagram here. So on my y-axis there, I've got boiling point in degrees Celsius. 20 degrees Celsius is roughly room temperature. So let's take a look at methane. Methane has a boiling point of minus 161 degrees Celsius. So above that, as we get warmer, it'll turn into a gas. And below that, as we get cooler, it's a liquid, until, of course, it'll turn into a solid. Now, methanol is its corresponding alcohol, and that has a boiling point of 64 degrees Celsius. So that's considerably higher. Now, what's the reason for that? Well, the answer is in the structure. If you look at methane, well, there's methane there. You should know that structure from chapter 8. And here is methanol. As we've our structure of methanol. I've expanded out the OH group there, as you can see. Now, the oxygen is a very, very electronegative element, and we know that when hydrogen is bonded to oxygen, we can get hydrogen bonds because of a delta plus on the hydrogen and a delta minus on the oxygen. In other words, the polar bond, the polar oxygen hydrogen bond. So in other words, if there's a nearby methanol molecule, or indeed a water molecule, for instance, the delta plus of one molecule, the partial positive hydrogen atom of one molecule can be attracted to the delta minus oxygen of another methanol molecule. And that is, of course, called a hydrogen bond. What do we know about hydrogen bonds? They're very strong. They elevate the boiling points of substances considerably. So the question we need to be asking ourselves is, why does methanol have a much higher boiling point than methane? Well, there's a couple of reasons. One, methanol has a higher relative molecular mass. Okay, that's due to the extra oxygen atom. Higher relative molecular mass means greater van der Waals forces strength, but the main reason is that the intermolecular forces between methanol molecules, the hydrogen bonds, are much stronger than those between methane molecules, which are just weaker van der Waals forces. There's no hydrogen bonds in the alkanes. They're all non-polar molecules. So we'll get a similar scenario occurring when we take ethane. Ethane boils or turns into a gas at minus 89 degrees Celsius, so it's a gas of room temperature. Ethanol turns vaporous at 78 degrees Celsius. Propane turns into a gas at minus 42 degrees Celsius. Its corresponding alcohol, if you like, propanol, evaporates at 97 degrees Celsius. Butane will evaporate at minus 1 degree Celsius, and butanol will evaporate at 117 degrees Celsius. Now you'll notice that there's something happening here. If you look at the difference between methane and methanol, the boiling point difference is 225 degrees Celsius. Whereas if you look at butane and butanol, the difference is much less. It's 118 degrees Celsius. So why is the difference much less when we look at butane relative to methanol and methane? Well, the reason is because in butanol, the hydrogen bonds are much weaker. And that's because, and you'll see this diagram in your notes, if you look at a molecule of butanol, most of it here, this end here, this hydrocarbon end here is non-polar. And it is, as the non-polar component gets bigger and bigger as you go through the alcohols, well then it takes on the form mainly of a non-polar molecule, even though it has a non-polar end. So this water molecule here, for instance, you can see it will find it very, very difficult to form hydrogen bonds because of this sort of what we call steric hindrance, blocking out the formation of the hydrogen bond, if you like, between the delta plus of this hydrogen here and the delta minus of the oxygen at the far end of the butanol molecule. So as a consequence, even though butanol can form hydrogen bonds, it can only do so if the water molecule or another butanol molecule happens to be in the right place at the right time. And water, in actual fact, has very, very poor solubility in water. It's only around 8% soluble, whereas methanol, ethanol, and propanol, the other three alcohols we discussed now, are infinitely soluble, should I say, in water. It's more about the alcohols. They're classified as very, very weak acids. They're extremely weak acids. They're so weak, in fact, they don't turn litmus red, blue litmus paper red. So very, very weak acids. And as we'll find out later on this section, or in this chapter, they are oxidized to form aldehydes or ketones. Don't worry about that too much for the moment. Go ahead and attempt question 271, please.